Welcome, everyone, to another session on Dr. Liu's VCE Physics channel. In this video, we'll be tackling the gravitation and planet motion from the NHT 2024 Physics examination. I'll be guiding you through the solutions and concepts, and I encourage all teachers, parents, and fellow students to contribute any insights or corrections you may have. With two satellites of equal mass in different circular Earth orbits, their speeds dictate their orbital radii, not their mass. This confirms that different speeds mean different radii. Option A is correct. Different radii imply different gravitational forces. D incorrect, as force is inversely proportional to the square of the radius. Kepler's laws dictate that different radii lead to different orbital periods. C incorrect, due to the square of the period being proportional to the cube of the radius. Finally, their differing speeds, despite identical mass, mean their kinetic energies are also different. B incorrect. For a GPS satellite in a circular Earth orbit, its velocity constantly changes direction even though its speed, magnitude of velocity, remains constant. As momentum is a vector quantity defined as the product of mass and velocity, the satellite's momentum is continuously changing due to the changing direction of its velocity. However, kinetic energy is a scalar quantity, calculated from the mass and the square of the speed. Since both the satellite's mass and its speed are constant, its kinetic energy remains constant. Since the satellite's orbital radius from the Earth's center is known, the strength of Earth's gravitational field at that radius can be calculated using the universal gravitational equation. The Earth's gravitational force is the sole force acting on this satellite, serving as the necessary centripetal force for its circular orbit. This means the gravitational acceleration at the satellite's specific radius is equivalent to its centripetal acceleration. We can then combine and rearrange the relevant equations, using the gravitational acceleration calculated in question 2a, not the surface value, to solve for the orbital period. Juan incorrectly calculated the satellite's gravitational potential energy by using the surface gravitational acceleration instead of the gravitational acceleration at the satellite's location. This is wrong because, at its high orbit, the gravitational acceleration is significantly lower than at the Earth's surface. This section, contributing 9 marks, 6.9% of the total 130 marks, assesses understanding of gravitation and planetary motion through 2 multiple-choice questions and 1 short-answer question. Multiple-choice questions, 2 marks total. Question 4 explores the relationship between speed and orbital radius for 2 satellites of identical mass, but differing speeds. It requires an explanation of why distinct speeds necessitate different radii and result in varying gravitational forces. Question 10 focuses on the kinetic energy and momentum of the GPS satellite in Marsat 4. The question asks for an explanation of why its kinetic energy remains constant, while its momentum changes due to the continuous alteration in the direction of its velocity. Short answer questions, 7 marks total. Question 4a requires the calculation of Earth's gravitational field strength at the orbital radius of the Himawari 8 satellite. Question 4b involves the calculation of the Himawari 8 satellite's orbital period, demonstrating that it is precisely 24 hours. Question 4c asks for an analysis of the common error of incorrectly applying the gravitational potential energy formula for the Himawari 8 satellite in orbit. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.